Okay. All right. Good morning, everybody. Today we want to talk about a new concept called trusted execution environments. Before that, we have a few slides remaining from our last topic on malware. So we're going to finish that, and then we're going to switch to trusted execution environments. Quick recap of what we did. Before that, just repeating what I said last time. Hopefully now you should be able to see the slots for submitting your papers. Is there anybody who cannot see it? Okay. So yeah, as I said, pick two of those three and submit yours. Just make sure that you're submitting it in the correct one. And two separate PDF files. It would be great if you can actually put your name down on your PDF file as well. Use the template that I put in the first lecture. And yeah, that's it for the paper reviews. Any questions about that? All right. And paper presentation starts next Tuesday. Probably I start with lecturing for an hour and then do the presentation, or we might do it the other way around, depends. I think next week we have Chintia, you will present. Who's the third group who's going to present? Oh, you guys present. Everybody know and ready and okay, right? Cool. Question? Yeah.
Is there like a rubric posted that we can use to follow like when we're creating our slides?
So I gave you the instructions of like what your slide should look like. So for creating your slide, use that. I'll also try to post some basic rubric for like how I'll grade it. But generally, if you follow those guidelines, you'll get the full thing. Okay. Any other questions about presentation? And then your first quiz would be this Friday. Those of you who couldn't make it, we'll be doing it on Monday. I guess a few of you. Just email me to make sure that I can send you the links. All right. Any other questions about anything? Oh yeah.
Yes, what material does it list on?
Oh, so everything until the month, everything including Monday lecture, not anything that I'll say today, and not the papers. Okay. So lecture 1 to 5, and that's it. Okay. Cool. So malware analysis, we said that essentially, we start with statically, bringing computers in the states that we want, known good states that we know that it's not been modified. Then the problem becomes that when we're starting running programs, then you have interaction between the device, the hardware, and the outside world. That outside world would be inputs and outputs, network, or even other processes, right? And that interaction creates problems, create opportunity for the attacker to attack the system, to infiltrate the system, and eventually take over or do something malicious. We said that essentially there are two main steps for any attacks, right? First step is somehow infiltrating the systems, get inside the system, right? And that should be through some I/O or some memory or some network. And we said that we're going to cover that part slightly later in the course. But once we do that, the second step is really what we're going to do with it, right? So what is the goal of the attacker eventually? And we said that essentially what we're looking for is what is called creating and executing a payload. And payload was eventually becomes a piece of software, which we usually call malware. So just generally, the definition is like any sort of piece of software that is being created to create some harm, to do some harm to the system, right? And we talked about 10 different types of malware, viruses, worms, trojans, etc., etc. I'm not going to go through them again, but generally the idea was, depending on the goals that they're trying to achieve and the way that they're influencing the system, the way that they spread themselves in the systems, that's usually the difference between each of these groups of malware. All right. And then the last one was like kind of interesting was wireless malware, which we're going to revisit again when we're talking about memory safety and security. Okay. All right. So last thing that we wanted to discuss, I want to continue on this in this lecture, was how to create and how to defend malware. And we said that generally defending against malware is a very difficult challenge because you want to defend against all of these malware, right? So it's not enough to say that, oh, my system is secure against ransomware, but it's not secure against viruses, right? So you want a holistic approach. You want something that's kind of like address all these problems. And you basically have two options, right? You have to prevent from being attacked by malware, or if you are actually attacked by malware, you need some sort of detection mechanism to at least catch it early on before it making huge damages. For prevention, we talked about good practices and so on. For detection, we essentially going to have two different options. One is the static analysis, which essentially we just look at our memory, because that's the part that programs can eventually run things from, and we start scanning the memory or the network, trying to see some known signatures, and those known signatures are sort of malware or viruses that we have seen before. And what we are trying to find is some sort of patterns. As I said, usually these big companies that produce this antivirus software. Okay. So, okay. There is this different companies that has this large set of databases for known malwares, and they very quickly and rapidly update their database as soon as they see a new type of malware. And what they do is basically then it's kind of like becomes a pattern matching kind of problem that you need to find those patterns in your system. The second approach is what's called a dynamic analysis. So unfortunately, static analysis has two major problems. One is it's only after the fact, and the second is finding those patterns may not be a simple task to do. So what you want to do is kind of like having a dynamic mechanism as well to, if the system is kind of like being attacked, you can quickly detect that. The idea of dynamic analysis is basically what's called an anomaly detection. So you kind of like, the basic idea is that you have some sort of like a good known model, you have some reference behavior, and what you do is that you continuously monitor the system, the behavior of the system, and if you see there is a difference, there is a deviation, or there is an anomaly from this behavior, you will report it as potential anomaly, all right, or potential malware. So you basically need to follow 4 steps, right? So you first need to pick what are those behavior, what are those features that you want to monitor from your system. We're going to talk about this later in the next slide. Then when you pick those, then you need to some sort of build a reference model for your system. So you need to kind of model as comprehensively and as big as coverage as you can, in order to say that, okay, these are the range of things that is normal for this device. Once you have those 2 things, now you're ready to kind of monitor the system. So you start monitoring. So you need a dynamic mechanism to execute programs, to get these features that you have selected, and then you need to constantly measure and compare these new metrics that you receive during the execution with the reference model that you have.
Isn't that similar to the static detection, or no?
It's kind of similar, but the difference is that this is as the program is being executed, you're looking at these features.
Does this static checking only check for hardware, or does it also check for software?
So usually static, basically what it does is looking at instructions. So it doesn't look at the hardware part. It's just basically looking at sequence of instructions or pattern in your instructions to detect that. Yeah. But for anomaly detection, for dynamic analysis, you can also then bring on dynamic features such as things like about your microarchitecture, things about your hardware, and so on and so forth. So that's why dynamic analysis is a little bit more richer in terms of the features that you can actually monitor.
And all the virus detection softwares don't check for dynamic anomalies.
Say it again.
Like the softwares for virus detection, they don't check for dynamic.
It's not like they don't check, they cannot, right? So the idea of static is this. So you have a piece of software, which is your antivirus, right? This is just a piece of software. And then you have your entire hard drive or DRAM or whatever you want to check. What this antivirus does usually is just go through your content of the memory line by line, and then build some sort of a model of either a transition model between each line or just checking the contents. And what it's trying to do is trying to see if they see the pattern. So let's say, for example, if I see the 100 instructions next to each other, that's a potential ransomware or something like that. Okay. So it's just basically, that's why we call it static. So it's not, there's no notion of executing the instructions. So there's no notion of hardware or features or metrics. We just basically go through the content of the memory. That's usually the idea for antivirus, for static analysis. The concept of static means that you're not running any program. And when we are talking about the dynamic is when we actually run programs, and while we are running programs, so it's kind of like becomes two parallel processes. One is the actual programs that's being running, and this would be your malware analysis or dynamic analysis. So it's kind of like, there is a relationship, there is a kind of like back and forth between these two in order to detect.
Okay, and who provides the malware analysis, like dynamic one?
So you are the ones that so for example, if your system you want to make sure that your system is not being attacked, you will actually implement that in your system. So for example, these days, Microsoft devices coming with dynamic malware analysis, part of the operating system itself.
Oh,
So usually the operating system, or sometimes this the core, the hardware does this for you.
okay, thank you.
Does dynamic detection have like a performance overhead as compared to static?
Yes, exactly. We're gonna actually cover that. We're good? So I'd like to actually go through the details of this, so to answer some of these questions. So things like features, what the model to use, how to compare, and things like that. Okay. So, and then actually, I think some of you who already started reading the papers, you will see that the majority of the papers is actually going to be about these things. So you can actually get some examples of real world scenarios how they tackle this problem. All right. So the first question is what features to use. Remember, we said that the very first thing is that we have a piece of software that we run, and we want to extract some features from this, which is kind of indicative of the behavior of the system. All right. So usually there are multiple different things that people look at. So network activity is one of the key things. So like, what sort of commands are being received or sent from a device. That's usually a very good indication of whether the system is being attacked, especially if you are worried about malware that's targeting the network. So if malware wants to penetrate the system, it has to come from the network. So if you actually monitor network behavior, we can kind of get this information. So what exactly are we looking at? So there are various things that you can look at, like packet size, number of packets, headers, things like that. So the frequency where you send things and so on and so forth. The second feature that you typically can look at is physical characteristics and physical attributes of the system. Actually, one of the papers that you're going to read is talking about what's called electromagnetic emanation. So the idea is that as your device is starting, executing instructions, there is this physical behavior that causes emanations of electromagnetics out of the device, because basically your transistors are switching, and as a result of the switching, you'll see electromagnetic signals coming out of it. And since this signal that you're receiving is kind of correlated with your behavior, with the instructions that are being executed, the signal is actually a good reference for what's going on inside the system. And what you can do is that looking at the signal, we run your normal program and say, okay, this is the normal behavior, and now I'm looking at abnormal behavior, right? And then basically this can be extended to any other physical characteristics of the signal, including the RF signal, including power consumption, and so on and so forth. So there is actually a large body of work that look at these different problems. Okay. Then there is another family of features that we can look at, and that's usually software characteristics. So things like different instructions, system calls, different functions, what function call we are using, and all these things. So think about all those different various things that you can look at in your software. That's all of those can be used for feature extraction. So for example, there are works that shows that if you look at the function calls and if you see the normal function call activity, it's the potential for possible in that. Okay. And then you can also go deeper and do what's called a hardware malware detector. Is actually a paper, one of the papers you're going to read is going to be about this. So you can look at the actual hardware activity in your systems. There are various things that you can look at the hardware level. Things like your memory activity, cache misses, branch prediction, branch misprediction, number of branches, number of your, for example, adding, multiplying, and all those things. So you can basically build a very, very rich model of all these activities in your system. And then if you see the deviation from that, you will report it as possible in that. Okay? Any questions here? So now that we know what sort of features we are going to get, so the question is, okay, how do we build our reference model? So to build that, this problem becomes kind of like a mixture of signal processing and these days machine learning, really. So what you're dealing with is kind of like sequence of some sort of a time series signal, right? So let's say, for example, we are looking at number of jumps in your program, right? So you basically have jumps at different time frames or a specific sampling time, right? And then you want to see whether this is an anomalous behavior or whether this is a normal behavior. So there are methods mainly developing there. Early on, it was at the signal processing level, but these days, mainly machine learning and deep learning and neural networks, where the idea is you build a model based on these features and label it as malicious or not malicious. And then what happens during the actual execution time, we get another set of features and feed it to your network, and then the network will say whether this is malicious. Okay. So it's kind of like, you build this model, that's the inputs to your system. So it's usually a set of features. And then usually you have a yes, no answer most of the time. And you train the system, so this would be during your training. So you get, your reference file, you get your training, and now you have your trained model. Okay. And now what you can do is that you use this trained model to monitor the behavior of the system during the actual malware detection time. So now you get new features, but you don't know whether these features are malicious or not. But your model is now trained so it can give you an answer whether this is yes or whether this is no, right? And if it's yes, it means that, for example, it's malicious. So now it's time to actually do something about it. If it's no, then you can just discard and move on. And you continuously do that, right? And if your model is trained well, then the chance that you detect the malware would be pretty, right? Of course, you cannot reach to 100% accuracy, but you can reach very, very high level of accuracy. Does this make sense? Okay, so that's usually the model we use. As I said, usually, as you will see in the papers that you're going to read, is these days machine learning, specifically neural networks, is the main way. But you can also do other things like decision trees, logistic regression, and things like that. So in order to build model, there are lots of things that you need to think about. One of the key things is what's called a coverage. So coverage means that, seeing all the different patterns from your normal activity. Why does it matter? It matters because it reduces it increases the accuracy of your system. So for example, let's say you have a program that has various different behaviors. Let's call it 1, 2, 3, all the way to n. And what you need, when you're training your model, of course, what you ideally want to do is being able to see all these different patterns, right? Because then your model will learn all those patterns, and then during the actual monitoring time, it can see those and it can detect, right? But in order to see all those patterns, think about this as a piece of software that has many different paths and many different activities. So you really need to generate inputs in order to have that coverage, right? So, for example, think about software that you have written. If there's like multiple different function calls, but it's not all the function calls have been always called, right? It depends on your input. Sometimes you call some of your functions, and sometimes you call the other set of functions, right? So you need to kind of like play with your inputs until you actually you see all these possible ways of running this program. And this is usually very, very difficult thing to do because the number of possibilities for a complex application is in order of 100,000 or even millions, right? So generating those inputs is not something trivial. But what you want to do is coming up with a mechanism to at least have some sort of good coverage, okay? And I mean, there are lots of, at the software engineering level, there are lots of, methods for creating this good coverage. We don't have to cover that, but just keep in mind that this is a big problem if people actually do extensive work on this, okay?
So is coverage also important so that doesn't view an unknown path as an anomaly? Even though
Yes,
the path-
so I mean, on the flip side, if you don't have enough coverage, then it could be a legitimate software that you think this is an anomaly because you haven't seen it during your training, right? So that's the problem with the coverage. So if you have a poor coverage, then your system will label things as anomalous, which indeed is not anomalous. It's just things that you haven't seen during the training. Does that make sense? And then somebody asked this question, like the overhead, right? So you continuously run this thing with your system, and of course this has overhead, multiple overheads. One is the storage overhead because this model has to be stored somewhere, right? So if it's a big model, you have to store it somewhere, so there is area overhead associated with this. The second problem is performance overheads because this has to be run with your system. For addressing the performance overhead, usually what you do is that run this in parallel with your actual application. So what it does is basically it doesn't really slow down your original application because it's just reading things on the side. So it doesn't really change the behavior of your original application. What it does is reading those things off of the system using some sort of registers or some sort of platform. But generally, it sometimes can slow down the system because it takes away some of the resources in your system. So potentially it can create some issues. Okay. So we have our features, the build our reference model. Now the question is that we have this reference model. We want to look at this system during the what's called inference time, right? So this would be the inference. This is the time that we actually want to see whether indeed we have a malware situation, we have a malware attack. Okay, so now this is kind of like a decision-making process, right? We see this process. How do we compare this process, this set of features with the set of features that we have seen during our training? And usually this involves some sort of decision-making process. There are various methods for it, extensively discussed in the literature. Usually there is some sort of statistical test people use. So the idea is that we kind of like look at the distribution of the inference, the features during the inference time. We look at the distribution of what we got during the testing time, and this is the inference time. And then there are tests that kind of like compare these two distributions and give you an answer of yes or no, kind of, which basically saying that are these two distributions are basically coming from the same distribution or not. They're fundamentally two different distributions. And with that, you can kind of say that, oh, this is actually indeed a malware. Okay. Another way, as I said, is pure machine learning. So you can use something like a neural net. Those of you who are familiar with neural nets, basically you can have like a complex, networks of nets that kind of like connected to each other layer by layer until it actually have a final layer, which usually can be a classification problem. In this case, we typically look at two different classes, right? We look at yes or no. So what it does is basically gets these features. There are some weights from one neural to neural network, neurons to another neuron. And then this way, eventually we get some values for yes and some values for no. And then we can make a decision whether this is malicious or not. So like usually what happens is that you get a very high value for one of them, a very low value for the other one. And this way you can make a decision that whether this is malicious. Okay. If you read one of those papers, you probably see more details on that. I intentionally didn't give you more details. One thing to keep in mind is that essentially we are dealing with this problem of true positive versus false positive, right? So true positive is what we really want. So it basically means that we actually detect malwares correctly. It's positive, which means it's malware, and it's true because it's actually indeed malware. False positive is the ones that it's not a malware, but we think it is a malware. So it's basically legitimate piece of software that our system unfortunately label as malware. And this is what we don't want to see, right? And then we're also gonna have false negative and true negative. Same story here. So true negative is actually legitimate software that our system also correctly labeled as not malicious. So we like that. But false negative is those that we think that it's not malware, but it's indeed malware. So this is the most dangerous one, and we have to be very careful to minimize the false negative as much as possible. The ones that we kind of like, hard to actually reduce is this false positive things, which, your system is very, very sensitive that even there are some legitimate software, it thinks that it's actually malware. And to fix this issue, you can do multiple things. You can use metrics that are less sensitive to your changes. But if you play with that number, then your false negative also might increase, right? So you say that, okay, I'm gonna label less of the things as malicious, and this way I'm reducing my false positive. But on the other hand, you also let some of the real malwares also goes undetected. So it's kind of like a game between false positive and false negative, and true positive and true negative. And whatever the system and metric you use, you have to be careful of all these 4 different things for a system. So all of them actually do matter. It's not like, oh, I only care about true positive and nothing else. That's not the correct decision. Okay. Any questions here? And final thing is that, okay, what should we do once the malware is detected? So let's say that we actually, our system with one way or another detect that this is indeed a malware. What should we do? Multiple things that you can do. Usually what happens is that you're reporting it to like some higher upper level hierarchy. This higher level hierarchy could be actually within the system. So for example, if you have a hardware malware detector, you report it to maybe operating system. And then maybe the operating system reported to the network, maybe the network send the data out to some central control. And that central control is actually indeed a human is sitting there and making some decision. Sometimes that decision is actually completely digital, which means that, for example, the operating system sees that this is a malware. So it's immediately, for example, shut down the entire application or shut down even the computer and so on and so forth. So there are multiple, ways of tackling this problem. Yeah. HMD hardware malware detector. So there are multiple ways of detecting and reacting this problem, but as I said, usually involves reporting into some higher level hierarchy. Even when it goes to human, it could be an IT person who's like, just get this message. That person can also go to the chain of commands in their entity or in their company and so on. So call it their manager, the manager call their manager, and so on and so on. So it's really what should be done depends on what sort of activity we do. If the activity is very, very security critical, then you want to minimize this response time as much as possible. So you're probably dealing with something that's purely digital. So like as soon as we see something malicious, we just shut down everything. But on the other hand, think about true false positive rate as well, right? So if our system thinks that it sees a malware, but indeed it's not a malware, and we shut down the system, that's a huge inconvenience, right? So you don't want to also be very aggressive on that part as well. So there's a game between being conservative and being aggressive as well. depending on how well your system can detect malware and how security critical your system is, okay? So for example, in your PC, you usually see that, oh, you get some messages or your system is just giving you a note that, you know what, this specific folder looks malicious, so we just quarantine it for you so you can no longer access it until we do more analysis and so on. But as I said, for example, a nuclear power plant, as soon as they see a potential attack, they probably just shut down the entire network, they shut down the entire power, they shut down the entire, lodging system and so on and so forth, because that's very different than the PC. Okay? Another question? And another thing to keep in mind is that, remember I told you that, we do usually multi-layer defense. So for malware detection is actually one of the key ways of protecting the system. So you usually don't have just one malware detector. You have malware detectors at multiple different layers. So you have at the software, you have at the OS, you have at the hardware. You might have multiple levels of malware detector. And what it does is basically, for example, if this is your lowest level malware detector, if it sees the malware, then it reports it to the higher level malware detector, the operating system. And then maybe the operating system does a little bit more tasks on it. And then if it also sees the malware, then send it to the higher level and higher level. So this way, the chances that they can actually detect malware with high accuracy becomes much more higher. Okay. So final things about malware before we switching on to the new concept is, now we said that, okay, we collect these features, we build our model and so on and so forth, and then we are able to detect malware. What the problem might be is that the adversary also might know this, right? So the adversary might know that you are using a malware detector, you are training your malware detector using some sort of reference model and so on. So what they can do is that they can adaptively change their malware to fool your malware detector as well. So like it becomes like an iterative process where the victim or the defender, get some features, train the model, use this model for inference, right? But the attacker sees that there is a model like this, so they actually change their features so that it agrees with these features here. So they actually pass the test of the malware detection. And then in that case, the defender needs to update their model using this newer set of malware, and then this kind of like it becomes an arm race between the attacker and the defender. We usually call this evasive malwares. So evasive malwares is this type of malware that knows that there is a malware detector, so it actually adaptively changes the behavior of the malware in order to become more stealthy. Same scenario with biological viruses, right? Like you have normal corona, then you have alpha, beta, etc. versions, right? So they actually adaptively. So your body actually being able to detect the first one, but it mutates and improves so that your body cannot react to it, and then your body again catch up and it can react to the newer version, and then newer variant comes, right? So same story for malwares as well, unfortunately. So the attacker can be intelligent, can be adaptive, and they can change their systems. And again, I think one of the papers we're going to talk about malware evasion, malwares, the scheme, and then how we can actually create malware detectors that are evasive resistance. All right, so it's actually evolved itself over and over time. So that if the adversary is also evasive, the malware detectors is aware of that evasion. Okay. Any questions? All right, so that's it for our malware analysis. We kind of like talked about why it's important, what are the different things that we need to care about. And as I said, huge body of work is on defending against these malwares. And that's usually what's called a malware detector, various ways of it at the software, at the operating system, at the hardware. So hopefully you read these papers and you get a little bit more information and details about these and challenges that comes with. Okay. All right. So now it's time to switch gear and then go back to the stories that we've been telling so far. And we want to talk about what's called trusted execution environments, all right? Maybe have a 2-minute break before we actually jump into this one. Okay. So going back to what we started really, we said that the idea of trusting a computer starts with trusting something inside the computer called TPM. Then we use a method for bootstrapping or chaining this trust. And then we kind of get this trust and load our system software or operating system, and now we are at that point, right? So now we have fully loaded our operating system in some known good state. And by the way, if the system does not have operating system, usually there is some sort of either real-time system, or there's some tiny OS, or in some cases there's just a basic system software. In any of those cases, we are loading some program that is the beginning and the initialization of our system. And that program takes control at that point, right? So then we need to continue. And once we run that program, which whether it's an operating system or not, the rest of it is just the dynamic behavior. You might call another program, you might run multiple applications, and so on and so forth. And the question is, okay, how do we guarantee the correctness of those activities? And we unfortunately cannot really do that. Well, because if we add more and more things to our boot sequence gets extremely slow, and that's not what you want. And another thing is that all these programs has dynamic features in them, so it's not something that you know beforehand what is the correct response or what is the correct reference for this, right? So you cannot really include that in your, for example, hash function computation and so on, right? So that method does not unfortunately work. So what we can do instead is what we want to discuss now. So the first thing is, if you want to run some application securely, which means that we want to make sure that this application is not being compromised, we have basically two options, right? So whether we can trust the operating system or system software, and in that case, we basically use the same idea that we use for TPM. So remember, we trust TPM and we use TPM to verify, for example, the operating system, right? So what we can do is that if we have the operating system and we can trust the operating system, we can ask the operating system to verify that application for us, right? And then we can move on next to the next one and next one. So the beauty of this is that the only thing that the TPM and the boot sequence needs to verify really is only part of the kernel. And then after that, once the operating system takes over, everything else is being verified by the operating system itself, right? This way, we kind of for the boot sequence, we have a very tiny part that we need to trust. Rest of it is actually being dealt with the operating system. But the problem really is that in many cases, the operating system itself cannot be trusted. Why? Because all of these attacks that we're talking about, really what it does is the first thing that it does is compromising critical functions and functionalities in your operating system. So there are many scenarios that you cannot really trust your operating system. And you're kind of looking in this adversarial setting that you want to run something in your computer, but you don't trust anybody, right? The only thing that you trusted was that piece of TPM, which no longer is active, kind of, because the only way that your TPM is active is during your boot sequence. So you want to run something, but now you're in this adversarial setting. So what should we do, right? Yeah.
Did we establish that we trust the OS because the whole boot sequence?
Yeah, we trust the beginning of the OS. So we trust the initialization of the OS. Now the OS, for example, runs for a few hours or a few days, and it's keep interacting with the network, with the IO, and so on and so forth. And then one way or another, some of these malwares that we discussed manage to penetrate into our system and then takes control. Now what? So now that there might be a chance that there is a malware in our system, what can we do to still be able to run things securely in our system, right? So that's the question. And the answer to that is we need a mechanism to kind of remotely or from the outside of this computer establish the trust, all right? And this is a very interesting, capability that we can have, because what it does say is, even if I don't trust my operating system, I still can use this computer in a useful and effective manner. Okay, we're going to talk about the second approach and what we're doing with it. Any question here? Other question? No? So the idea of this is what's called trusted. You had a question?
I was just gonna ask a clarification question. So the TPM, is that so that we can trust the initialization of the OS?
Yes.
But what would happen if you like do it with like Linux?
You reboot it. You can reboot it. Yeah.
You boot it with like Linux, then how would it trust the OS if it's like not with it or something like that? Or would it still be with it?
Repeat the question again.
If like say if I do boot my computer with Linux, how would I be able to like trust the OS? Would TPM so somehow not be able to touch that?
Oh, you mean if you have two multiple operating
Yeah.
system, how does it work? So your TPM can be extended to multiple operating system, right? But you remember the way that your TPM worked was basically, stored some hash functions, right? So you can, if you have multiple of them, you can store multiple hashes with it. There are some details that we're not gonna go, but at the very high level, that's the idea. So it's not really limited by the number of operating systems that you have. Another thing that you can do, you can always boot the kernel of your, for example, Windows, and then ask that to load your Linux kernel, for example. That's usually, so typically you have like one thing in between called hypervisor. So you load your hypervisor, and your hypervisor actually loads your operating system. So you trust your hypervisor instead of your operating system. Make sense? Okay. So now we want to see how we actually get this outside trust, and the idea of this is what's called trusted execution environments, all right, or Ts. So T is basically saying that we have this piece of hardware, we have this tiny thing TPM that we can trust, and we use that to kind of load, and this is our memory. And then we use that to kind of trust partially part of this memory that hosts our operating system, right? And then after that, we really don't trust this rest of the things because this rest of the things is controlled by the operating system, and we cannot really just verify everything into our memory because our memory is huge and things are dynamically changing. So it's not an option to just verify the entire memory. Okay. So that's the way that we are working right now. So the idea of the trusted execution environment is that saying that, let's actually reserve maybe a tiny space in this part and just don't let operating system to change anything here. This part will be reserved by another piece of hardware, which we call the T. And this T is gonna basically manage and moderate these things in our system. And we're going to create a mechanism that enables this T to talk to the outside world, so we can give some access to the network. So remote user can basically directly talk to the T to send and receive some commands and run some execution and some. All right. And this way, if we load the system, we trust this, but at some point the OS no longer can be trusted. So all these things are potentially malicious, but we will create a hardware mechanism that makes sure that the OS cannot, attack or change things at this part of the memory. So this is basically a physical isolation that we create at the hardware level in order to make sure that even if the operating system is compromised, that part of the memory can never be replaced or be modified by anything except this piece of hardware. And again, the same way that we're trusting the TPM, we are trusting this T environment as well. This is, again, additional piece of hardware that we literally physically put in our system. And this way, we get the guarantees the same way that you're getting guarantees for TPM. Okay? So in other words, T is kind of like the interactive version of the TPM, and we're going to discuss how exactly this is being implemented. There are various options for implementing this. And in the next part of the lecture, I'm going to just discuss the details and how we, in reality, we implement this. Okay?
I didn't exactly understand why we need the T as compared to the TPM.
Because TPM is not an interactive thing, so it's basically just gives you the the secure boot sequence. Actually, when I'm describing the way that we're gonna implement T, you will see what is the difference. So we actually started. I mean, the timeline was we started from TPM and we saw that TPM is not enough, and that's why we added T. So maybe wait a little bit. Once I go through the steps, you will see why we need T in addition to TPM. But as I said, genuinely think about T as an interactive version of TPM. Mentally, if you want to think that these are the same things, it's okay. Both of them are kind of part of the reserved hardware, but TPM specifically is just module that gives you some very basic functionality, which is just a secure.
And so TPM is like the thing that guarantees your OS is not corrupted on the start, right?
Exactly, yeah.
So then, does the T, like, when you say dynamic detector, does it mean like when the OS is running, it keeps on checking whether there's any malware injected into it, or?
Basically, the idea is that your malware cannot infect your T memory because your T memory is only communicated with specific user from the outside. So even if your operating system is talking to the network, to the other user, your T is kind of isolated completely from this environment. So when the malware takes over, it takes over the memory, but since the T part is reserved and is isolated, cannot be changed. Does that make sense?
Does the TE also guarantee OS not being corrupted on the startup like TPM, or is it?
Yeah, it does. See, actually, there is a mechanism for doing that. I'll talk about it. We're good? Okay, so let's actually go through details to answer some of these questions. So basically, there are two use cases for T. For now, what I discuss is this trusted computing. There is another use case for T, which is called confidential computing, which later at the end of the lecture, if we have time, I'm going to talk about it. In fact, actually, one of your papers is about this second part, the confidential computing. So I'm going to discuss why T's could be useful for confidential computing as well. But for now, let's focus on this one. Okay, so let's actually go through the details. So the concept of T is what I said, but there is actually various different implementation and various different design choices. And things like Intel SGX and ARM Trust Zones are the main two options that you will see. Trust Zone actually recently got updated to this confidential compute something, ARM CCA. So this is like a brand new version that's ARM very recently just released. So it's kind of like the updated version of Trust Zone. So we're going to talk about the SGX and Trust Zone. And then there's also a whole bunch of other methods that's been proposed by academia, lots of different papers. You will actually read one of those papers called Sanctuary. That's kind of like, kind of build off on the top of Trust Zone and add this additional functionality. Once I describe what these are, you will also understand what that is, okay? But just for now, keep in mind that, in order to realize T, you can have multiple options, all right? So some terminology that we're going to use when we are talking about these various options. The first one is TCB, or Trusted Computing Base. All right. So TCB is what we start from. Like, remember I said that we basically verify the initial version. So that's your TCB. That's the base that you kind of trust, and everything else kind of build off of that. What you want usually is having very small TCB, because TCB has to be verified by hardware. And everything else is being verified by your TCB. So if you have a large program, you verify TCB by your hardware, as we'll discuss later, and then the rest of the program is basically verified by TCB. Okay, so it's kind of like the way that we are doing this. But for now, know that when I'm saying about trusted computing base, I'm talking about this part that's being verified by your hardware. Then there's the notion of measuring and sealing. So when we are saying measuring, it means that we want to see whether the software is compromised or not. And this process requires computing the hash of that value and then comparing that hash with the correct hash.
So what exactly is the trusted computing base? Is it like a software thing or a hardware thing?
Yes, it could be a hardware thing, could be a hard software thing. Usually when we're saying TCP, we're talking about the actual software. So measuring is basically this. So for example, let's say your TCP is a piece of software. And then you have a hardware that wants to measure whether this can be trusted or not, right? So we want to answer this question that this is trusted or not. So how do we do the measuring? Basically, measuring involves some sort of computing the hash or the content of this piece of software, this piece of memory. So as I said before, think about this as each line is basically a value. So we compute the hash of this value, and now you know how to compute hash, right? So we compute the hash of this, and then that would be the inputs to the next version. So hash of this, and then so on and so forth. So we just the inputs of the first one would be the output of the first line would be the input of the next line plus the value and so on and so forth. So remember the way that I said, how do we do cascaded hash, right? So this is exactly where we're going to use that. So the beginning, we do hash, you go to the next step, and next step. And at the end of the day, you get one final hash value, right, of this program P. Oops. And that would be the value that you are getting from this program. So let's call it A, for example. What you do is that you are comparing A with the correct value of A or CA or whatever you want to call it. If these two matches, it means that this program can be trusted. If they don't match, it means that this program cannot be trusted. Okay? So one more time, when we are doing measuring, basically this piece of hardware has this CA already, this correct A. What it does is basically go and compute the hash of this value one by one. How do we compute the hash? We discussed it, how do we cascade multiple lines. So we go through that line by line. Eventually we get the final hash value, which we call it A. Then we get this A, we compare this A with this value that we have pre-stored. If these two matches, it means that this value, this software has not been modified. We can trust it, and then we can move. Okay, so usually this process is called measuring. All right, so we measure different software or different part of the hardware if need be, and basically use that in order to see whether we can trust that or not. Does it make sense? Any questions for measuring?
So what is that pre-stored hash computed for software?
When we are developing the software, so the actual developer of that software needs to create that hash for us. Right? So we're assuming that the designer is not malicious, right? So, I mean, if it's a 0 day, remember we said there are 0 day problems. So if there are 0 day problems, obviously this does not fix that. But if you're assuming that the problems come from this fact that things being modified along the way, this hash value can help us with that. Okay. All right, so this is measuring. So if you heard that I'm saying measuring, this is what it means. And then there's the concept of sealing. So sealing means usually when we want to send something to the outside world, we usually do take multiple things. So for example, we encrypt it, we put a MAC with it. Sometimes we also sign it. So all these different things. So we kind of package this value when we are sending it. And this is usually called sealing. In most of the cases, when we are saying sealing, it means that we encrypt the data, we also add a MAC to it. So we basically do authenticated encryption, okay? So when we're saying that, for example, this value has been sealed, it means that we did this, okay? And then finally, root of trust is where we build our trust off of. So for example, the root of trust usually is hardware, some sort of hardware, and then we build off our trust based on that, okay? So we have the root of trust. Using the root of trust, we build our TCP. Using our TCP, we start measuring things, and then once we measure them, we can trust. Okay, so this is kind of like the step-by-step level. Any questions from these terminologies?
Could you explain sealing
Sealing means that when you're sending or receiving messages, so whether it's from, for example, one piece of software to another piece of software, or from the hardware to TCP, or from the inside the computer to the outside of the computer, if we are doing encryption in MAC, most of the cases, then that's what we are calling sealing. So we don't send the original hash, we usually encrypt it or using authentication encryption and then send it out. So that if somebody in between sees that, doesn't understand anything about it.
So we first encrypt and then we compute the hash, right?
Yes. No, we compute the hash internally. Instead of sending the hash value to the outside, we encrypt it and then send it. So in this case, your hash is your message. You want to protect it, right?
I thought in the previous lecture you said this is acceptable to attach.
No, that was for MAC and message. So what we said last time was, if you have a message and you make sure that the integrity of your message is not being compromised, you should not compute the MAC of this message and then encrypt it. That's not the correct way to do it, okay? What you need to do is that you have to encrypt it and then compute the MAC over the encryption. Okay, that's the correct way to do it. What I'm saying here is that your M is basically the hash of your program. It's basically your this. Okay, so you first compute the hash. That will be your message. You need to seal your message before sending it out. Okay. Any other questions here? So the things that we're going to discuss, the difference between SGX and TrustZone, and as I said, these different design choices that we have, is because of these main three things that we're going to discuss: the size of your TCP, and then generally how you build your TCP, the overhead that comes with your system, and then generally the capabilities that you're going to use. We're going to actually discuss this, so let me actually just go into the details about this. So this is kind of like, how, to have a mental model of how the T works. This is basically how T would work. So you have your trusted computing base, right? This is the part that you trust. Then you build off of that what's called dynamic root of trust. You basically, you add more and more services to your system. And then if you have any secure programs or secure modules, SM1, SM2, we call it secure modules, you basically, from this dynamic root of trust, you measure it. So you measure this secure module using this dynamic root of trust. If it's actually trusted, then this becomes also part of your trusted environment. And then when you want to talk to your outside world, you use this method called attestation, which we're going to talk about. We actually talked about it before. And then if you want to store something, you don't just directly store it, you seal things and then store it. All right. And then on next to these things, you also have your untrusted apps here. All right. So again, this red part would be your trusted domain, and this non-red part would be your untrusted domain. You will have multiple apps that are not necessarily part of your trusted execution environments, and that's totally normal. You have your trusted computing base, which is the beginning of your system, where you put your trust. You use that to, as I said, you build off of your trust. So you add additional, functionalities, and you call it dynamic root of trust. The reason that we call it dynamic is that at the beginning, this part was not trusted, but we use our TCP to trust those parts. So now it's part of our root, right? So it's a dynamic part of our root. So DROT. And then we have a bunch of different applications: secure module 1, secure module 2, secure module 3, all the way to end, whatever we have. In order to trust these parts, we need to do the measuring. And I just described what measuring is. And once we do that, then they also become part of our DROT, all right? They become part of our dynamic root of trust. And then if you want to send and receive things to the outside world, you have to do the sealing. And then if a remote user wants to communicate with us, they have to use this notion called attestation, which I'm gonna describe. Okay? And this part and this part does not have any interaction. Okay? For now, there is no interaction between these two. So you can also have your normal world application, which basically does not have any impact on your secure world application.
So is the end goal here for the remote user to find out if the system is trustworthy, or for the system to find out if the remote user is trustworthy?
No, the end goal is that this user can run the secure modules in the system. So at the end of the day, what we want to do is being able to execute this.
Okay, so it's to find out if the system is trustworthy?
Yes. So, or in other words, the system is not trustworthy, but we want to run our program in an untrustworthy environment.
Makes
So
sense.
we always trust this part. So this remote user, let me use another color maybe. This remote user trusts this part here. These two always trust each other. The rest of this is just mechanism that we create, that we first trust this part, then this part trusts this part, and now we can basically, the remote user can run this secure module on this untrusted. But the remote user cannot, for example, run this app because it has no idea that whether this app can be trusted or not.
Thank you.
Why do we say remote user?
Because the user is not part of the operating system. So remember, we are talking about this scenario that the operating system may or may not be compromised. So anything within that operating system can no longer be trusted. So if you want to run something, we have to be outside that operating system. So it's either physically separated, which is usually the case, or it's just another piece of, another operating system that's talking to this operating system.
Go over what part of this is the dynamic root of trust.
What part of it?
What part of this diagram would be dynamic?
So generally, the dynamic root of trust means that, remember, essentially we started with TCP. That was the only part that we trust. And dynamic root of trust is generally this notion that, as we do measuring, we adding more and more modules to our trusted zone. And we call that dynamic root of trust because at the beginning, our root of trust was only our TCP, but we dynamically expand that root of trust to other modules, okay? So for example, this module could be a service module that does the measuring for us. So it could be a hash function, for example, right? Initially, the hash function wasn't part of our TCP because we want to keep our TCP small. So we trust the TCP trusts the hash function. So now the hash function can be trusted, okay? And then you can infinitely increase your dynamic root of trust essentially, because as long as you trust this can verify this can verify that, and so on and so forth. So you can expand your dynamic root of trust. Okay.
Like there's applications that are expanded to the dynamic root of trust.
Yes, they can be technically. The reason that we don't put it as the notation that I'm using here is that these modules come and go. So they're like only transient. So you run some application, you're done with that application, and you go to another application. Your hash function always stays. So for the entire lifetime of your dynamic root of trust kind of lives, but your secure modules kind of come and go. So you run one application, you jump to another application, and so on and so forth. But generally, all of these is part of your dynamic root of trust. So at this specific snapshot that I'm showing here, you can also assume that your SM1 and SM2 is also part of the DRO. Okay.
So from the perspective of the user, they can add, like, if assuming they have the permission and stuff, they can add any application to the system, and then the next time they try to use it, this will ensure that that application is
Yeah,
secure.
we're actually going to go through the steps of how to add a new application.
Okay, cool. Thank you.
Okay. So going back to this attestation parts, I already discussed what was attestation, but one more time. So basically, attestation is this challenge response paradigm, right? So what you do is you have a piece of program, right, with multiple different lines, and you have another user. So this is usually called verifier. And this is device under test or device under test or prover they call it. Okay, so we don't trust this. And the goal is that whether this verifier which we trust and trust this or not. Okay, so this process is called attestation. So we want to test whether this thing can be trusted. How do we do that? The verifier sends what's called a challenge. Okay, so a very basic thing, the challenge could be just set of addresses. Basically, the verifier asks the prover, give me the hash code of line X to line Y. Okay, so just go into these lines of your memory, compute the hash of this, and send me back the hash. Okay, so the challenge usually is the first step is sending the challenge, which is usually like some sort of values. Okay, so we send it to the prover. The prover has to compute the hash over this challenge, and then send the hash value back. Okay. Obviously, the verifier has the copy of this memory, so internally it also computes the hash, and then compare this hash with this hash that's being sent by the device. If these two matches, it means that this part of the program or this user can be trusted. Usually, a challenge response is multiple steps, so it's not just one challenge. It's multiple challenges because the attacker can be very stealthy and very smart and then tries to actually give you correct answer. But when you increase the number of challenges, the chances significantly reduce. Another thing for as a session to remember is that you usually, in order to eliminate the chance of replay attacks, because if I send the same challenge, I get the same response, and the attacker can change things but give me the correct response. So similar to the way that we use encryption, we also include some nonce. So anytime that we send a challenge, we send a new nonce. And for the hash function, the attacker, the prover has to first compute the hash of the nonce and then add it to their challenge. So basically, each time the hash that comes out is different than the previous time, even though that you send the exact same challenge. Okay, so this process is called attestation. So the challenge response paradigm, the verifier sends some challenges, which is basically just asking the prover to compute some hash over their memory. The prover needs to quickly do that, send back the results. If the results is correct, then you can trust it. Okay, so this is the process of attestation. And why attestation is important, because essentially if you want to, for example, if the remote user wants to know whether their SM2 or SM1 has not been modified, they can actually do the attestation. So in this case, the remote becomes the verifier, and this SM becomes the prover. Okay. So basically what we want to know as a remote user, we want to make sure that this software that we want to execute on this computer has not been modified, right? So we use this process of attestation in order to get it. Okay.
So like when the verifier like trusted the software initially, it computed like those hashes to like know what the challenge hash should be, so they can later compare it.
The verifier can either on the fly or pre-compute. Either works. Usually it's on the fly. So because the same time it takes for the prover to compute the hash, in parallel the verifier can also compute the hash. But it could be pre-computed as well, because remember the verifier can send same challenges over and over again. So they can only need to compute hash one time. And then it just change the nonce and then send it again, right? So. Is that clear what the attestation is? Any questions here? Okay. So now we have all the tools. Let's actually talk about the actual implementation. We're going to start with SGX. So in order to understand why we need SGX, and as actually you guys already asked this, you have to look at the TPM and see what is the use case of the TPM. Remember, we said TPM was this very tiny piece of hardware that all it does is was some hash function and some keys, right? And that's basically it, right? And all it does is basically once we boot the system, we ask this TPM to compute the hash of the very first part of the boot sequence, right? So it does compute the hash of this. It sees that whether this is modified or not. If it is okay, then we could basically go to the next steps of our boot sequence. Here again, this part now computes the hash of this part, send this hash value to our TPM. Our TPM again look into the pre-stored hash values. If it's matched, then it says okay, goes to the next step, and next step, right? And then that was where we get our operating system and go with it. The problem is that we cannot really add all those, so once we are at this point, we cannot really start new application because we don't have the correct hash value of those applications here, right? So what we can do is that the first things that Intel specifically, because Intel was kind of like creator of this, was thinking about is this technology called TXT. So the TXT technology was the first attempt to create keys, and the idea was that what we can do is once we boot the system and then we want to run something, what we can do is basically just delete everything from our system and then boot the system into some known good state and just give the control to that specific program. So basically what we do is that, let's say we have some pre-computed applications. If the user wants to run those applications, all that they need to do is reboot the system and just completely, delete the entire memory or sanitize the entire memory and load this application into our memory. And then just exclusively give all the access of the inputs and outputs and everything to this specific application. And then this way we kind of guarantee that this application is secure because the operating system cannot modify anything because we can basically reboot the system into that specific boot known state. And everything, including all the resources, including the I/O network, and everything is only can communicate with this specific application and nothing else in notebook. And then if you want to go back to our normal execution, we again have to reboot the system, delete entirely this part of the memory, go back and load our operating system here, and then continue. And then if you want to switch back and forth, this process happens over and over again. We reboot the system, we sanitize the entire memory, we load the application that we want, and we continue. Okay, so that was kind of like providing this ability that specific application can get the entire control of the system. And backed by the design of the TPM, we can actually guarantee that this indeed can happen. So we can create a boot sequence, but instead of booting the operating system, we can boot whatever application that the user wants, right? So, and then we can give exclusive access to that application for that user. Okay, so that was the idea of the Intel TXT technology. And it works actually, it's quite secure, as secure as the way that we are loading the operating system. The problem though was basically a huge overhead that comes with this approach, right? So remember that anytime that we want to run something securely, we kind of need to pause and just get rid of the entire, memory and then load the new application and run that application. And it's only single threaded, right? So we basically can only run one application at a time on our system. We cannot, for example, do other things that are not trusted with the same trusted, application that we have, okay? And also there is no notion of like an interaction between this software and other software because that's the only software that's being executed on our system, okay? So that's kind of like, the initial idea, and it works for some specific scenarios, right? So for example, if if your system is for some reason is only multitask, it's a single task system and you don't, regularly, switch back and forth between applications, that's actually quite effective because it gives you the guarantee that you want. It basically gives you an unlimited access to multiple different operating systems in some sense. It's not really that, but in some sense. So that was kind of the initial idea, but that was not good enough because these days we are working with multitask systems. We want to have interaction between multiple applications, and we also want to be able to run not trusted applications with trusted applications at the same time, really. Because maybe some user is more important than the other users. So those users needs the assurance of trusted execution environments, but the other user doesn't care. The application that they do run is not something that's security critical. So because of that demand, the idea of software guard extension or SGX comes into the play for Intel. And the idea for Intel is basically instead of like having one TXT, having a bunch of different TXTs. And they call that enclave, hardware enclave, all right? So these are basically isolated modules that you can basically, instead of like creating one TXT, maybe you can create multiple of these TXTs, okay? So to understand how do we create this isolation, I need to give you a little bit background on, in general, how do we create isolation in our memory, in our systems. Those of you who have done, who have taken, computer architecture course recently, probably, hopefully you remember, but that's the moment of truth for you guys. Okay, so to understand how do we create isolation and why isolation is important, you need to look at the main memory, look at the memory of the system and think about how our programs are kind of like, being put into this main memory. So what we usually do is that, we put different programs into different parts of the main memory, and the critical thing that we need to care about is that there should be isolation between these programs. Why? Because we don't want to let people. Good? Yeah. We don't want program 1 to be able to change values in program B, right? Or program 2 or program 3. Because if it does, then it's very easy for an attacker to change things, right? This would be a malicious program, and all it does is start not only changing things in its own address space, but also changing things in the other address space. So very basic things that we need to do is that being able to kind of block any sort of access from one program to other programs. Okay, so we definitely need this. And then if you think about programs, generally programs has different regions. So when I'm showing this continuous part of the program, what really this has is kind of like different sections. For Intel system, you usually see code, data, heap, stack. So kind of like, a system like this that has this different regions. Usually most of these code and data is kind of like predefined, size are usually fixed. But the heap and stack is kind of like something that is growing. So usually one in one direction and the other is in the other direction. And usually this space here is some free space. So your stack can grow in one direction and your heap can grow in the other direction. You might fill your entire memory with that, and that's where you can no longer grow your stack. Your operating system will throw an error. But most of the cases, you have enough space to grow in this direction. All right. Another idea that you can do is that while you're doing this isolation, you can actually share some part of the memory between users. So you can say that, okay, this part can actually be read by all the users. So I'm not going to block the access to this part. And this can be used for communication, for accessing shared libraries, and so on. So for example, your SD, your standard libraries in your code is stored somewhere here, and it's only one copy of that. Anybody who wants to use printf or scanf and so on, you have to go into this part of your main memory to bring those things. Okay. And what another thing that we usually do, we usually reserve part of the memory for the operating system and privileged access. So basically think about the operating system as another program, and we reserve part of the memory for the operating system. Okay, it's kind of like the design of our memory and the way that we kind of design this. So So now think about how do we actually partition? How do we decide that program 1 sits here, program 2 sits here, program 3 sits here, and so on and so forth. And in order to understand that, the first very simple thing is that, okay, I'm going to statically, partition my memory into the pieces. And this way I'm going to say, okay, X amount of memory is for program 1, and Y amount of memory is program 2, so on and so forth. Maybe this part is shared, and we're done with it, right? The problem with this is that if we are adding more program, then we run into a bunch of different problems, right? The first is that if we kind of like, already divided the entire memory into the existing programs, there's no space for program 3 to just, fit into our memory, right? The second problem is that, when you're statically, assign parts to your memory, then if one program for some reason wants to grow or wants to shrink, you're not, effectively using your memory, or you either don't have enough space for the program to expand, or you just wasting some part of your memory. Okay, so static is not a great idea. So what you need to do is what's called a dynamic way of sharing and partitioning your memory, and that's what we do these days on our advanced operating systems. Okay, and how do we do it? We actually do it with this concept called paging. Okay, so page is like, remember I said that, we have program 1, program 2, program 3, and so on. What we're gonna do is that we're gonna break down these programs into smaller pieces, in smaller basic blocks called page, okay? So for example, program A might have 4 different pages and so on. This page is something that is fixed, and you know it beforehand. Usually in most standard systems, it's only 4 kilobytes of data, okay? So you say that every 4 kilobytes, we call it page, and we're gonna name it. We're gonna page number 1, page number 2, page number 3 for program 1. Then we have page number 1, page number 2, page number 3 for program 2, so on and so forth for all of them. How would this help? So as I said, usually we use this as 4 kilobytes. So basically, if you want to address this memory, all you need to do is using the lower 12 bits of your address to find that page, right? So 0, 0 all the way to 0, it means page 1. If you do 1, means page 2, and so on and so on. Okay. So going back here, how do we use these pages in order to scatter this into our main memory, and how would this help us to dynamically partition our memory? Well, what we will gotta do is that instead of like, assigning continuous parts for each program and pre-assign this into specific fixed size, we're going to scatter these pages into our program. So basically our memory becomes this basic block-based kind of thing that it can just, think about this as an array where each content of the array, each index of our array becomes one page. And what happens is that you no longer need to just store everything into same place. You can just, store it wherever you want. And now if, for example, programs see that, I need another page as well. I need to grow. I need page number 4. I'm going to go through this memory and find the first place that there's an empty space for a page. I'm going to name this page 4 with the purple, or program C page 4. Okay. And then the operating system will also use these pages. Okay, so everybody is going to use the same notion of pages. And if I have another program D, again, I'm going to put page 0, program D maybe here, page number 1 here, page number 2 here, 3 here, and so on and so forth. Of course, at some point, my memory might be full, and at that point, we can no longer accept new programs. So we need to kind of like kick out something. But that's not an issue for now, at least. Okay, so we basically usually think about this as your main memory is big enough that it can host all of your programs all at the same time, and that's usually the case. And in reality, you have your hard drive, which kind of like helps as a backend to your main memory. But for now, think about that. Your main memory is so big that you always have space for some new pages. Okay, and that's not a very wrong assumption. Okay. So now that we have this page concept, we can kind of like deal with the shrinkage or expansion. We can deal with new programs and old programs. And then if this program for some reason it's no longer is active, we can then go and free the spaces here, 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 here and then we can assign a new page. Okay. So it's kind of like what I just described. Pages are pretty fixed. They can go into the different directions and so on. Any questions at this point? Okay. The problem with this approach is tracking where your page is, right? So since I said that, I can, store this page anywhere in my memory. So next time I actually wants to read something from my page 0, I need to know where I stored that page, right? And that's a big challenge because this page technically can be anywhere in the memory, and I cannot go and search, every individual line in the memory to know where it is. Okay. So how do we fix this? We fix this by storing the mapping of our pages to our main memory. And we usually call this page table, okay? So basically what we do is that we have a very small table, which is much more smaller than the actual, contents of our page. And we say that, your page 0 was stored at this address. And we usually only need to store the beginning of the address. Everything else can be offsetted by that, right? And then we do it for every single page that we have in this program. And for every single program that we have, we also have a separate page table, right? And this page table itself is not something big, it's something very small. So we can have like a separate storage maybe for it to have this page table. And this way, when I want to access something maybe in this page, what I do is that I have to go first to my page table to get this address, and then use this address to go to this part. Okay, so this way kind of like store some sort of a key or some sort of a map that anytime that I want to read something, I have to go to the page table first, see what is the actual address, and then go to that address. Okay, and because of this kind of translation between two different addresses, we usually call this virtual address or VA, and we call this physical address or PA. Okay, so virtual address is the addresses that our software understands. It basically say, okay, I'm in this program, and the first thing I'm going to do is like reading this, reading that, and so on. So that's my page number 0, page number 1, and so on. So I have a system of addressing my program that has nothing to do with the other programs, and we call that virtual address. The operating system understands each program separately and creates a separate virtual physical table for it, this page table for it. So as soon as this software wants to read something, the operating system sends this virtual address request to this page table. This page table does a translation for it, right? So basically it's translate this virtual address to this physical address by just going and looking up where this page has been stored. And at that point, we have what's called the physical address. This is literally the address that this value has been stored. It's literally go into that line in the main memory, bring data back to the program, and everybody is happy. Okay?
So is the location of each page table also stored somewhere?
Location of each page table is stored somewhere. For now, don't worry about where the page table is stored. But page table itself is stored as part of the operating system. Okay. So this is the notion of what's called the virtual addressing. Okay. The reason for virtual addressing is that each software does not need to deal with the actual location of their physical pages. They can just, live without the knowledge of where their data are stored. They can start with address 0 and go to all the way to address n. And next program can also start from address 0, go to all the way address n. There could be this, at first look, they're the same addresses, but in reality, this is the virtual address of process 1. This is the virtual address of process 2. When they are actually being translated, they translate into separate physical addresses, and that's how we actually deal with different addresses in our main. Okay. Any questions? Did you guys remember this? Those of you who took the course. All right. So as I said, this is the concept of what's called a virtual address. Essentially, we start with address 000. each program think that it has a uniform access to entire memory. So addresses is starting like, incrementally goes from 0, 0 to maybe 0, 1, and 0, 2, 0, 3, and so on and so forth. So each program thinks that it has a uniform continuous memory. But in reality, this is not what's really happening, because this address then gets translated to physical address, and maybe even your two continuous addresses might actually be mapped into very, very different physical addresses. But as long as the programming standing points or software standing points, we don't care. We just rather write our programs as the way we do, right? We say A0, A1, A2. In reality, these are very separate addresses, but we don't care, okay? So as I said, this is basically the virtual to physical address translation. And basically, this would be the life cycle of a program. We have a program. Each program has its own set of virtual addresses. There is a translation here using a page table to get the physical address. Now we have a physical address. We can go to our main memory, read back data, and bring the data back to our program. Okay, and this would be for each program. So how does this relate to security? How do we do the isolation in this case? The isolation actually, the magic happens during the translation, okay? So when we are doing the translation from virtual to physical, as I said, we have actually a table that has entries, right? Each entry is basically a physical page number. So the indexes are virtual addresses. So this is, for example, 0, 1, 2, 3, and so on and so forth. And this is actually the physical address here. But on top of, in addition to this physical addresses, we have usually another set of columns called flags, which this flags is basically giving you an idea that who has access to this page, who has access to this part of our physical memory. And here we can, for example, say that, this different process IDs has access to this. We can also say that, for example, process number 1 has read and write access, but maybe process number 2 has only read access. Maybe we can say process number 3 has read, write, and execution access, but the others cannot execute things. So execution means that you can actually treat this as a program and then start executing things off of it. And then you can do all sort of these different flags as you want to, okay? And if necessary, you can even add more flags. So basically, the isolation happens during this translation. That when program wants to access specific physical address, we go to that physical address and check this flag and see whether that process is actually authorized to access that specific page. If it's not, then the operating system throws an error, right? Something like segmentation fault or some other traps, other exceptions. So some sort of exceptions will be thrown, and the operating system will block that access. Okay, so this is how operating system is basically operates and doesn't let different programs access each other. Okay, so now we have this background. We need to go back and see what is the relationship between this address translation and our trusted execution environments, because in the trusted execution environments, we're kind of using the same thing. Any questions here? Okay. So now let's go back. So for Intel SGX, remember I said that the idea is we want to have multiple of this, what's called an enclave. Remember at the beginning I said that T is basically saying this, that majority of the memory can be accessed by the operating system, but maybe we can reserve some part of the memory and does not allow the operating system to access this part. Okay, so how do we do that? That's exactly what we're going to do. So we're going to say that, so this is our physical memory, by the way. So what we're going to do is that for the page tables, we're going to have two separate page tables. Page table number 1 is going to be accessible by the operating system, and that's actually the addresses that maps into this region. And this another page table is specifically for this range of the addresses. And this part cannot be addressed and cannot be accessed by the operating system. Who handles this? Our specialized hardware or the T access this page table. So if you need address translation for this portion of the memory, if we query the operating system and ask that, you know what, give me the address translation and give me the content of this part of the memory, this T is going to block that because essentially the operating system does not know exactly where this is located. Okay, so this part of the page table is actually mapped to this page table here, and that's controlled by the trusted execution environment. So we basically, separating the control of our address translation into two separate modules. The majority of it is controlled by the operating system. The minority of it, which is the reserved part, is actually controlled by our trusted execution environment. Okay, and this way we can actually get the isolation that we want, so that even though that the operating system has control and has been compromised, physically they cannot modify anything in this portion of the memory. Why? Because they don't have the translation for it. They don't know where it is. Okay, so that's how we actually give this guarantee. Physically, this is how it's actually being mapped. So essentially what we have is that this is our DRAM, this is our physical memory. Portion of this memory is actually what's called the PRM or reserved memory for physical reserved memory for our T. Within this PRM is this thing called EPC or enclave cache, physical cache, which is usually almost the entire part of the PRM, but there are other things that we don't care about for now. This EPC, which is basically part of the PRM. PRM is this physical reserved memory, which is reserved for the T. Within PRM, there's this thing called enclave physical cache, which is used for the enclaves. And remember, we said that we don't want to have only one enclave. We want to be able to have multiple enclaves. So that's why what we do in the EPC is that, remember the same way that I said that we're going to have multiple programs and we're going to do the paging for accessing multiple programs. The same idea is used here. So in our EPC, we actually have the paging notion, and each of these can belong to a separate enclave. So with this trick, we actually reserve some part of the memory. So we know that only T can access that. But within that reserved part, we actually do the paging. And with that paging, we can now have enclave number 1, enclave number 2, enclave number 3. So maybe this one and this one and this one is for program 0. And then maybe this one and this one is for program number 1. Okay, and then we can continue over and over. We can have multiple of these enclaves on our system, but all of them are secure because essentially it's part of the reserved memory that's only controlled by the trusted execution environment. And this is using the paging. So the page table within the T is actually controlling. Okay, is that clear? Any question? If you run out of pages, then you can no longer add an additional enclave. So basically, you're kind of limited by the number of enclaves that you can run in the system. So if you want to request a new enclave, you have to wait. Or one thing you can do is kind of evict some of these. So you need to kick out some of these and then run this. So typically, you can have something like a priority based, saying that this is number 0 priority, this is number 1 priority, and so on. And if a higher priority comes, you kick out things lower priority.
So you can't take it back to the hard drive.
You cannot kick it back because that's defeat the purpose, right? So so you just need to sanitize it to get rid of it. You cannot put it back to DRAM because then it basically means that now it will be controlled by the operating system. So you never know what's going to happen.
So if a program needs to expand and get more memory, how does the trusted execution environment securely add new pages to the enclave?
So again, this is the same way that the operating system handles those requests, the same way the trusted execution handles those requests. So usually, for example, there's usually an API that if you like the way that we request for new and free and request a new part of memory, same way you can do it for your trusted execution. If you look at the SGX specifically, there's a software manual for it, there's a set of APIs. So think about it the same way that you use, for example, free and new or creating a function. You have to use a specific, syntax for creating that for your SGX. But conceptually, it's just the exact same thing that you do for your normal operating system.
Thank you.
But biggest difference is that we only are working with small ratio of the entire DRAM. So in other words, the amount of memory available to your SGX is usually much smaller than your DRAM. So you cannot really run really large programs in your SGX, and you cannot really have many different, multi-programs in your SGX. You probably need only, kind of like limited by a small number of these applications. But that's typically is okay because you want to do limited things with your SGX. But that's a big limitation that we're gonna actually cover in the next slide. Are we good? Okay, so I guess that's a good time to stop here. We need to now, the only thing that more from SGX is that now we need to understand how do we create a new enclave and how do we get rid of the enclave. That's an important part that we need to